Hi everyone. Today I want to talk with you about your spring force lab. So this is the one where you were taking the hanging masses and you were hanging them on the end of a spring and you were measuring how much that spring stretched. So I want to start by drawing a free body diagram for our scenario so we can start to analyze what's going on here. We have a spring force pulling up on the mass. So our spring that we're hanging from would pull up. I'm going to label that Fs for F spring, okay? And then the hanging mass has mass, okay? So then if it has mass, it's going to have a force of gravity pulling it down towards the ground. So I have this force of spring that's upward and this force of gravity that's downward. And I'm going to say that the upward direction is positive and the downward direction is negative. Next thing I want to do is I want to sum my forces, or I want to find my net force. So you should have heard a little bit about this in the last video, okay? So we want to essentially add all of our forces up so we can start to analyze our scenario. Now, I know that this hanging mass is not moving, so that means that the force upward has to be equal to the force downward in order for that to happen. If the force upward was bigger, the mass would move up towards the sky. If the force of gravity was bigger, it would move down towards the ground, and neither one of those are happening. So that means that essentially this force of spring has to cancel out that force of gravity, which means when I sum these two, they need to add up to 0 because they need to cancel each other out. So when I do this summing part, where all I'm doing is adding, I'm going to take the positive force of spring and add it to the negative force of gravity, and that should be equal to 0. And that gives us a little mathematic relationship here to prove that I am saying that those two things are equal because my spring is not moving. Okay. I also want to draw a little picture of our scenario here so we can start defining some things. So we have this spring hanging from something, and I have a hanging mass on the end. Okay. Initially, before I put this mass onto the spring has some sort of natural length, is what I'm going to call it. So let's say the spring was hanging to this point right here before the mass. So I can refer to this as our initial position of the spring. And then I hang the mass onto it and the spring stretches. So then it stretches to a part down here. I'm going to draw it at the top of this little mass, the very tip of the spring, where I would have my final position of the spring. Okay, so this final position minus our initial position gives us the displacement of the end of the spring, and we're going to call that our stretch distance. So this is the distance you should have been using to make your graph of your force versus your stretch distance. So if we look at that graph that we made, the simulation asked you to make a graph of the force of gravity for the hanging masses, and remember that forces are measured in newtons, versus the stretch distance in meters. Okay, everyone should have gotten a straight line. However, everyone used a different spring. If I remember correctly, it had you split off from your birthdays. So some people got a graph with an intercept. So I'm going to draw it that way so we can kind of chat about what that intercept is. But either way, everyone should have gotten a straight line. Okay, and let's say our slope value. So I was kind of taking a little peruse at somebody's earlier, and I believe they got a slope of about 8.3. So just for visualization purposes, we'll use 8.3. Okay. Now, this intercept right here, this intercept would show us the force of gravity of the spring itself. So you can think of it as like an initial force of gravity, a force of gravity that would be there before we put any hanging masses into the system. Okay, I pulled up a simulation to hopefully help us with some visualization or as to why not everyone got an intercept. So not all springs are created equal. Some have a lot of mass, some have a little bit of mass. And those of you who had an intercept of 0 probably just had a spring that had a very small, basically negligible mass. So I'm going to use this slider over here that is labeled spring constant. And I want you to watch what happens to this spring when I slide it. So as I slide, deet, 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 okay, I have a really thin spring, okay, or I can have a really thick spring where this thick spring essentially has more mass. So if you ended up with an intercept, you just had a spring with more mass than some of your other friends who did this lab, okay? So if we come back here, look at the equation of our line, because we're going to use our equation to derive our equation of our line to derive an equation for the force from a spring, okay? I'm going to leave off the B because generally in AP Physics 1, we're going to use like a theoretically perfect spring that's going to be considered to be massless. So usually we just ignore the mass of the spring, simplify the scenario so we can boogie on with our lives, okay? So on the y-axis for now, I put the force of gravity, and then you had your slope value, and then on the x-axis you put your stretch distance. Now, I know that this spring, just a side note, was stretching in the y direction. In last unit, when something was moving in the y direction, we labeled that a delta y, okay? You're welcome to do so. However, generally when you see this equation that we're trying to derive here, it's just referred to as a delta x. No matter if it's in the x direction or the y direction, they just simplified it and left it as x. Just little side note there. So our force of gravity, though, I'm not trying to come up with an equation for the force of gravity. We already have one of those. But I am trying to come up with an equation for the force from a spring. And we said earlier the force from a spring in this scenario is equal to the force of gravity. So since those two are equal to each other, then I could replace force of gravity with force of spring. So this starts to look like an equation for the force of spring, not the force of gravity, okay? And now the last thing we have to figure out here is what this slope is telling us. So in order to do that, we always want to start by looking at the units for our slope. So the units, we would have a change in force over a change in meters, okay? Force has the unit of a Newton. I don't know why I put M. I think I was thinking ahead, right? So let's erase that. Change in force over a change in X. That's better. But our X is measured in meters. So this idea of a Newton per a meter, it's going to measure this special value that we're going to call K. All right. And K is something known as the spring constant. Okay. So if we flip back over here, we have this slider that I was sliding that said spring constant. Okay. So this is trying to help you visualize the idea of a spring constant. Now, while the spring constant really isn't a measurement of the mass of the spring, they're making it bigger and thinner to help you visualize that maybe this spring would be stiffer than this spring. So you've all played with a spring or a slinky or something in your life, and you know that not all springs stretch the same. Some are hard to stretch, some are easy to stretch. You can think of it as tight and loose, stiff and not stiff, does not matter, whatever makes you happy, but we can all visualize the fact that they do not stretch the same. So this spring constant is what is going to be a value to account for that. So if I think about this, it is showing me the amount of newtons needed to stretch that a certain meter amount, okay? So really stiff springs have a high K value or a high spring constant value. Really loose springs require less force to stretch them, so they have a smaller K. So when I'm thinking about the force that's being applied from a spring, I need to take into account the stiffness of the spring. So I have to add this spring constant in to help us make that determination and find that force. So spring constant. Now, it is called a constant. However, it is different for each spring. So every spring has its own value for a spring constant, but the spring constant is constant for that one spring. Okay. So we have our equation now for the force from a spring. Side note here, as we move on, this force from a spring, this equation, is going to be used for anything that's elastic and stretches. So any material that has any sort of stretch to it has a value that's equivalent to the thought of a spring constant, because not everything stretches the same. So we're generally going to use this as a force from a spring, okay? However, this relationship works for any material that stretches, okay? And then we have our stretch distance, or what we've been calling our stretch distance, but this could also be a compression distance. So we're about to do a little example here where if instead of stretching the spring, maybe I could compress it upwards, and that spring would still apply a force if it was being compressed in the same way that it would as if it was being stretched. So I'm going to label that for now as our stretch and compression distance, okay, because it can be either. Let's give ourselves a little space here. So where the scenario I'm going to use to talk about the difference between those two, it's kind of a twofer, because you'll see online this thing called Hooke's law. And Hooke's law is essentially the equation for the force from a spring. However, when you see it written, most commonly, it says the force of the spring is equal to negative K delta X. All right, so this negative is going to pop up a lot, and all it's saying is that it's there because the force and the compression or stretch distance are always going to be in opposite directions. So that negative is put there to denote the fact that if the force is positive, then the delta x must be negative, okay? The way that we are going to look at forces questions and the questions that we're going to have in our curriculum, you will just be using this equation without the negative, and this equation would really just give you the magnitude of the force from a spring. And we will add in this directionality part, which is what this negative is, as we go through and do the summing of our forces situation. Because you saw earlier when we drew a free body diagram and we summed our forces, we did look at positive versus negative. We already looked at the direction, okay? But just so we're all on the same page, I'm going to draw this hanging mass scenario two different ways. So the first one I'm going to draw as if the spring is compressed. And the second I'm going to draw as if the spring was stretched. Okay, so either way, I have a natural link to my spring. So let's say that my spring that I'm looking at here would naturally sit along this line. And we're going to call this our x is equal to 0 position, the 0 point where I can look and see if my displacement is positive or negative. And I'm going to say if you move upward from that line, that's going to be in the positive direction. So anything that moves from this blue line up to this black line that I'm going to use as my ceiling would be positive. And then if our spring were to move downward, I would say that it from this blue line to wherever it ends, I'm going to call that the negative direction. Okay. So for this first one, I have my spring, and yes, it is still attached to our mass, but instead of just letting the mass hang, I'm going to push that mass upward so that it causes this spring to be compressed. So then when I do so, if I'm looking at my final position here, if I'm saying that above the blue line is positive, then that means I would have a positive final position, okay? And then if I looked at my